Hello friends, welcome back to my channel. This is Tanneru Hemant Kumar, studying in Sri Venkateswara College of Engineering, Department of Computer Science and Engineering. Today our topic is generating the object code using SIC source program. Hello friends, welcome back to my channel. This is Tanneru Hemant Kumar, studying in Sri Venkateswara College of Engineering, Department of Computer Science and Engineering. Today our topic is generating the object code using SIC source program.
Hypothetical machine SIC, simplified instruction computers. Today we will discuss more about the second version of SIC machine, that is called SIC XE, simplified instructional computers extra equipment. It is a little more features are there compared to SIC. The memory of SIC XE is 1 megabyte, that is 20 bits are there to address the location from 0 to the last location 2 raised to 20 minus 1. So total 2 raised to 20 bytes we can store. It's also byte addressable memory. 1 byte of data at a time we can store, or we can load and store. And instruction format and addressing modes are little changes are there in the SIC XE machine compared to SIC machine. And in addition to the 5 register 24-bit register which is available in SIC machine, 4 more registers are there. B register number is 3. It is used for a base indexing purpose, so that register is called the base register. S is another register. 4 is the number, is a general purpose register used for general purpose arithmetic operation, etc. T is also a general purpose register. Its number is 5. F is a floating point accumulator. It's a 48-bit register and its number is 6. Here you can see that the register S and T are only for storing data. So one example, add register S, A. So in SIC XE machine, the data format is, it support all the data format which is available in SIC, and extra formats only we will discuss here. Since SIC XE machine support floating point arithmetic operation, so it support floating point data. So the floating point is a 48-bit type data type. So that floating point is represented like the first bit, MSB bit is sign bit, followed by 11 exponent bit, then the remaining 36 bits is for storing the fraction. So sign may be positive or negative, and fraction is a value that lies in between 0 and 1, and exponent E is always positive. It's an unsigned number, so you can represent any number between 0 to 2047 because 11 bits are there, 2 raised to 11 minus 1. So if you have a number that is represented by SEF, then the number is, the value of that number in floating point is S into EF into 2 raised to E minus 1024. For example, suppose 5 we can represent in binary as 101, that is 2 raised to 2 plus 2 raised to 0. So that we can represent another way as 2 raised to minus 1 plus 2 raised to minus 3 into 2 raised to 3, that is 2 raised to minus 1 plus 2 raised to 3, 2 raised to minus 3 into 2 raised to 1027 minus 1024. So this is the way to represent. So here you can see that 0 is represent a positive number, yes, 5 is a positive, then 1027 is represented here, and fraction number, actually fraction 0.5 is represented by using this representation. 2 raised to minus 1, that is first position. This is represent 2 raised to minus 1. This is represent 2 raised to minus 2. This is represent 2 raised to minus 3. So that's why 1 0 1, remaining all zeros. So this is a floating point number 5. Then instruction, next topic is instruction format of SIC. Since the memory used by SIC is of size 2 raised to 20 bytes, 1 megabytes. So the instruction format of SIC is not enough, because to address a location beyond 2 raised to 50, it's not possible in SIC, because maximum we have 2 raised to 15 bits. But we have in SIC we have 1 megabytes of locations, so we need little more bits in the address field. So this SIC machine support all the instruction format supported by its SIC machine. So one solution we can use as, one is extend the address field, second one use the relative addressing mode. Both these options are available in SIC. So the instruction format is broadly classified into 4 categories. First one is format 1. Format 1 instruction in SIC is of size 1 byte, only opcode. There are such instructions like return RS, return from subroutine, RSUB, that is the opcode. That is only we will mention in the instruction, in the programming. Then format 2 is 2 byte. So you can see that 8 bit is for representing opcode. Then 2 operand we can use, R1 and R2 of size 4 bits equal, and usually this R1 and R2 are operands are registers. In format 3 you can see that is a 3 bytes 24 bit instruction. So 6 bit is used for opcode, then 6 flag bits are there. So this flag bits has certain meaning. So while discussing addressing mode, we will look into what is this flag bits. Then remaining 12 displacement bits. There is a format 3 instruction in SIC. The next one is last one, format 4 is a 4 byte. So the total of size 32 bits. So here you can see that opcode is 6 bit, flag bits, then remaining 20 bits are used for addressing, specifying the operands, that is address. These are the major instruction format in SIC. Then addressing modes. Since it has different instruction formats, so it supports different type of addressing mode compared to SIC. All the addressing modes included in SIC is also included in SIC. Then 2 new addressing modes are relative addressing modes for format 3 instructions. So first we will see how we can identify format 3 instruction, its addressing modes. So there are 2 bits, flag bits B and P. If B indicate base addressing mode, base relative addressing mode, P indicate program counter relative addressing. If B is equal to 1 and P is equal to 0, then we can say that format 3 instruction is in base relative addressing mode. If P is equal to 1 and B is equal to 0, then we can tell that instruction, format 3 instruction, is in program counter relative addressing mode. Suppose if the instruction is in base relative, then how you can compute target address? Target address or effective address is equal to what is the content in base register plus displacement. The displacement in format 3 is of size 12 bits, so you can have a displacement of 0 to 4095 because 2 raised to 12 is 4096. A program counter addressing mode for the format 3 instruction, look at its target address is base register plus displacement. Here the base register is program counter. So displacement, so with respect to program counter position, you can forward or you can move backward. If you are moving forward, it's a positive advancement, so that's why you can move maximum of 2047 locations. If it is a backward move, it is a negative advancement, so that's why we will have a negative 2048 displacement maximum. So the displacement may, with respect to program counter, we will calculate. So it is from minus 2048 to plus 2047. When the base relative mode is used, the displacement is 12 bit unsigned integer, so that is why maximum of 4096. But when we are using program counter relative mode, the displacement is a 12 bit signed number, so 2's complement representation we will use. So that is why the displacement is from negative to positive maximum. So forward move and backward move both possible in program counter relative. If b is equal to 0 and p is equal to 0, then the addressing mode of format 3 instruction is direct addressing mode. Okay, this base relative and program counter relative addressing mode can combine with another flag bit, so that X indicate whether the instruction is in index addressing mode. If X is equal to 1, it is an index addressing mode. If X is equal to 0, it is not in index addressing mode. So if in this case, suppose here X is equal to 1, then you can tell, if X is equal to 1, then you can tell it is a base relative index addressing mode. If X is equal to 0, it is base relative addressing mode. Similarly, in the case of program counter relative mode, if X is equal to 1, you can tell the program counter relative and index addressing mode. If it is X is equal to 0, then it is program counter relative mode. So this is the meaning of B, P and X. Yes. Then look at here. To identify the instruction format, whether it is in format 3 or format 4, we will have one flag bit that is called E. Here you can see that E bit, 1 bit. If E is equal to 0, then the instruction is in format 3. When E is equal to 1, the instruction is in format 4. So E is over, P is for program relative, X is for base relative, and B is for base relative, X is for index addressing mode. The remaining 2 bits are N and I. So N and I we can see here. Bit X, B, P, E are already discussed. So that will represent relative, direct and index addressing mode. These are the 3 major class of addressing modes can be represented by using X, B, P and E of the format 3 or format 4. Then I and N is used for representing these class of addressing modes. If I equal to 1 and N is equal to 0, then the instruction is in immediate addressing mode. Suppose an instruction is in immediate addressing mode, then what is in the address, that itself is the operand. There is no memory reference, so that value exactly is used for performing the operation. There is no need for memory reference. If I is equal to 0 and N is equal to 1 indicate it's an indirect addressing mode, then the target address is calculated. The word at the target address is fetched. Okay. Then the value of target address is taken as the address of the operand. then only we will get an indirect addressing mode. We will explain this addressing mode with an example after finishing this class of addressing mode. Then the last one, if I is equal to 0, n is equal to 0, or both I and n is equal to 1, will represent simple addressing. If both 0, it is a standard SIC addressing mode. If both 1, then the target address is taken as the address of the operand value. There is no memory reference again. Exactly, memory reference is there, but there is no need for adding any base register or index register or program counter register, etc. Directly what is available in the target address, that itself we can take in as operand value. So these are the related direct addressing mode, indirect addressing mode, relative addressing mode, index addressing mode, and simple addressing mode. These are the class of addressing mode supported by SIC XC. Now look at here, we will explain this addressing mode with an example. Here I have shown here a memory, a portion of memory. So one location is 3030. The data present in this location is 003600. The next location is 3600. This memory location contain data 10300. Then 6390 contain this data, and C303 contain the data 003030. And there are 3 registers mentioned here. What is the content of that register? B is a base register contain 006000, and program counter contain 003000, and X, that means index register contain this value 00090. So please remember this value because we are calculating target address of the different type of instructions. Okay, so look at the first instruction. Here you can see that E is equal to 0. So if E is equal to 0, then it's a format 3 instruction. Then you can see that here 12-bit displacement, then 6-bit opcode, 6-bit flag fields. Yeah, then here you can see n is equal to 1, I is equal to 1. So n is equal to 1, I is equal to 1 means it's a simple addressing mode. So we have seen that if n is equal to 1, I is equal to 1, it is a simple addressing mode. Then this value represents, this is binary, so its hexa value is 0. So this 0 will represent first 0. Then all zeros means second 0 will represent. Then 0 1 1 0 represent 6. Then since it is a program counter relative, so program counter contain the value 003,000. Then the target address is 003,000 plus what is available in displacement. The displacement contain 0 6 0 0. So if you add these two values, which is equal to 0 0 6 3 0 0. So this is the target address. So target address is obtained. Then we will refer the memory. This location, this is the location obtained 003600. So that memory location contain 103000. That is the value we will get. Okay, so then what is the meaning of this opcode is, it is a load accumulator. So whatever present in target address is loaded into accumulator. So that is the meaning of this opcode. This is the instruction LDA, load accumulator. Okay, so first instruction is over. Second instruction is, look at here, E is equal to 0 means it's format 3 instruction. both n and I is equal to 1, so simple addressing mode, but b is equal to 1 and x is equal to 1, so indexed and base relative addressing mode. So the value is present in this displacement is 0, 0, 3, and what is in X register? So target address is calculated by using index register. Sorry, first we will use base register value plus index register value plus base register plus index register, then displacement value. This is the target address. You can see that our displacement is 300, and our X register contain 0090, and our base register contain 90. Base register contain 6000. So 6000 plus 0, X register contain 90. Only I will write only last 4 hexadecimal digit. Then what is in the displacement? 0, 3, 0, 0. If you add all these 3 values, then you will get 6390. Correct? Yeah, 6390. So the location 6390 contains 00C300 because opcode is same. So instruction is load accumulator. So what is content in 6390 is stored into accumulator. So this is the content. The next one is n is equal to 1 and e is equal to 0. So format 3 but indirect addressing mode. Look at here, this is very important. In this case the displacement is 0, so p is also 1. So program counter value we need to check. Program counter is 0, 0, 3, 0, 0, 0. The next one is, yeah, it is indirect. Then the displacement is 0, 0, 0, 0, 3, 0. This is the value. If you check it, you can see that 0, 3, 0. Okay, so if you add it, you will get 3, 3, 0, 3. The remaining is 2, 0. That means 0, 0, 3, 0, 3, 0. Correct? Then you refer that location. Yeah, this is the location. The value stored in that location is this one. It is indirect addressing mode. So we need to refer what is the value in the location 3600. So this is why it is called indirect addressing mode. So our target address is 3030. The target location contain the value 3600. Then read that value, and that would be our exact target address, and point to another location, and that location contain the value 103,000. So you can see here that is the value loaded into accumulators. So that is why we call it as an indirect addressing mode. Then this is, we can see that I is 1 immediate, so there is no change in that. Displacement is 30, so 30 is loaded into accumulator. Then this is a format for instruction is equal to 1, program counter displacement. Since the displacement is equal to 006 and program counter point to 3000, 3000 plus 600 is equal to 3600. So what is the value in 3600? This is the value. Okay, then last one is e is equal to 1, format 4, and this 2 is equal to 1 in symbol addressing mode. Then since the displacement is 5 into 4, 20 bit displacement, you can see 1, 4, 4, 4, 4, 4, so 20 bit. So this is equal to 3, 0, 3, and this is 12, actually C, hexadecimal value C, So C303, this is the target address because this is simple addressing mode. Then what is present in that C303, this is the value, so that is loaded into the accumulator. So these are the few set of instructions, and that instruction belongs to which addressing mode, and how the target address is calculated based on the addressing mode is explained in this table. Okay, this is another example we can work out. Yeah, so the next one is what are the instruction sets supported by SIC-XC. So SIC-XC will support all the instruction sets supported by SIC plus few additional instruction set. Okay, so what are the additional instruction set? Because there are 4 additional registers, so few additional instructions are there which will support those registers, like load B register, store B register, load X register, store X register, etc. Then since it is supporting floating point arithmetic operations, so there are few instructions which will support floating point operation, like add, subtract floating point number, add floating point number, multiply floating point number, etc. Next step, this SIC-XC machine support register to register operation, so that is represented by add R. Add R means add the register to register, and a special instruction is there, RMO, that is called register move operation. Okay, next one is a SEC instruction, the supervisor call. So whenever the assembler or the instruction or the program executing this SVC need any operating system supervisor call SVC, we use it to generate the interrupt, and that interrupt will help the program to call or take the service of operating system. So this is very important. So this type of instruction is used to access the service of operating system. Then what are the input output related operations? Apart from 3 instructions which is available in SIC, these SIC-XC have 3 more instructions that are called SIO, TIO and HIO. These SIO, TIO and HIO represent start, test and halt of the IO devices. The next one is instruction set. So this SIC support a wide range of instruction set. So whenever we require instruction from the instruction set, so that time we will explain more about those instruction set. Okay, so programming is not included in your scope of the discussion. So basically what we explained is the architecture of SIC-XC, simple instructional computer, extra equipments architecture. So this is a little more complex compared to SIC architecture. Okay, thank you for watching this video. So we will see you with another video.